Chat. Okay.
Hello everyone, welcome to Bangalore Theory Seminar Series. Today we are very excited to have Karthik Gajulapalli as our guest speaker. Karthik is fourth year PhD student at Georgetown University, where he is advised by Sasha Golovnev. He is interested in theoretical cryptography and complexity theory. Today he has very kindly agreed to talk on his exciting work titled Matrix Multiplication and Verification via Coding Theory. So let's welcome Karthik. Over to you.
Thank you, Kirtan, for the introduction. I'm most excited to be here. And this talk has nothing to do with cryptography and mostly nothing to do with complexity. This is everything to do with algorithms. So hopefully that is interesting to some people here. This is joint work with Huck, Sasha, and Evelyn. So I'm going to break the talk into these 5 parts. I'm going to introduce the problem for a little bit. I'm going to then talk about a special problem that is matrix verification. Then we're going to deal with matrix multiplication. And then we'll see some kind of barriers for proving why we can't come up with better algorithms. And we'll finally end with some open problems. Okay, so here's this problem we've all seen in high school. I want to multiply 2 matrices. What is the complexity it takes to multiply 2 matrices? Right, essentially I'm computing a bunch of dot products. I have n square cells. Each cell I'm computing a dot product. So it takes me, the trivial algorithm takes me like n cubed time. This is what we all learned in school, right? We just go like this, like this, like this. We do this n squared different times. Yeah. Okay. And so if I can multiply matrices faster, it turns out to be quite useful. First of all, almost every problem in linear algebra reduces to fast matrix multiplication. So if I want to compute the determinant, the inverse, LU factorization, any kind of linear algebra task I want reduces to multiply matrices fast. But more generally, like even graph problems, right? Shortest path, diameter, tether closing, maximum matching, all of these can be solved via fast matrix multiplication. But again, like that's not the field. Like you can keep going further and further, like ML, everywhere. Fast matrix multiplication is useful. And the question is, can we achieve it in linear time, which is O(n squared, because my matrices are n squared built. Now, I should also be careful. There are fast algorithms that we'll see them later, but none of them are practical. In practice, we still use the n-cube algorithms because the recursive factors, constant factors are so high that it's completely useless. But this is, we are theory people. We don't care about this, Like I'm going to hide log factors all over the place. Just that's the way we go. Okay, so what is omega? Omega is kind of our best upper bound. Some people believe omega to be 2. The best omega we have right now is 2.37. So initially, when they introduced matrices, that's when they were invented around 1850s. They had this n-cube algorithm already implicitly. And it took like almost 150 years before, or maybe 100 years, before Strassen came up with improvement. And this is starting like every undergrad algorithms class, right? You kind of have these blocks. You can shave in the block computation, and then like you recursively apply this a few times. You get down to n cubed to n to the 2.8. This is already non-trivial, right? Because I'm taking 2 n square matrices and I'm saying I can do something better than brute force, which was the dot product approach. And then like there was like further improvements, and then like you see how small the improvements are getting, but improvements till you get here. Okay? And that's the state of the art today. Now, this, if any of you guys have read Moby Dick, is a hard problem. And there are people much smarter trying to solve this. We're going to stick away from this. We're going to stick to like easy problems, simple things. Okay? We're not going to harpoon the whale, we're going to kind of swim around it. Okay? So we're going to look at the first thing we're going to look at is verification. I'm going to change the problem. I now give you 3 matrices, A, B, and C. And your job is to tell me whether the third matrix is a product of the first 2 matrices. Is AB equal to C? So again, my input is ABC. You have to output yes if AB is equal to C or not. Okay, problem makes sense? Okay, what's the trivial algorithm? I just multiply, right? I multiply the matrices, that runs an n omega, right? And then I check every entrance one at a time to see if it's correct. Can I do better? Does anybody know? Can we solve this problem better than n to the omega? Any ideas? The random what? Yeah, there's a randomized algorithm. And that was by Freivalds. I just multiply my matrices by a random vector. Okay. Why does this work? Well, essentially, like you can kind of catch if my product AB minus C is non-zero, then my random vector will catch it with probability 1/2. It's not very hard to see why this is true. Very simple algorithm. Huh? So what this is doing is it's checking if AB minus C is non-zero. If there is a non-zero point, then this random vector catches it with probability 1/2. Okay. And so my time is about n squared because essentially I can compute this first. This takes me only n squared time. Now I've collapsed a single column. So specifically I can do this, right? So I'm not multiplying my matrices. And the randomness is just O of n. Nice. So there is a randomized solution. And you can make this, you can use like, you can reduce the dependence on randomness. You can kind of think of this as a polynomial. And I only had a sample of prime, right? So you think of univariate polynomial instead of like a whole vector. So you can get the randomness down to log n, but the time is optimal because you need to read the matrices. That's n squared. So you can't do better. Okay. So the actual question is, I have a gap where n to the omega for deterministic, and I have, I have n to the omega for deterministic, and I have like n squared for randomness. Can I de-randomize Freivalds? This has been open since 79. Okay. And so the first result is exactly this. So what we show here is that if I have three matrices, A, B, and C, and actually the product C disagrees on a few points, a sparse set of points, then we can deterministically give an algorithm, we can tell you yes in something faster than brute force. If they disagree on many points, and this is slightly counterintuitive, we'll talk about this in a second, then we don't know how to answer this. So it is weird because we're saying when the product A, B, and C disagree a lot, we can't see anything. We're like pretty useless. But when they are like, when it's like they disagree on only 1 point or 2 points or a few points, like a sparse set of points, then we can actually say something. So it's weird. The statement is weird. It's unnatural, but maybe we'll see why in a second. A question before? Okay. Yeah. Which one? Yep, solve the dependent delta. Yeah. So when delta is equal to 2, we'll get omega. And when delta is less than 2, we'll get something better than. So if you think you can think of delta as 1.999, then we'll get an algorithm that's faster, better than omega. Omega minus something. Epsilon will depend on that. But when delta is equal to 2, omega epsilon 0. Okay. More questions? Okay, before we get started, let's maybe introduce a helper problem. I'm going to say, let's forget about this verification. Let's think of an even simpler problem. I'll give you two matrices. Tell me if their product is the all zeros matrix or not. That's it. So your input is two matrices. Tell me if they're, think of everything over a field. The results will carry over to like the integers. But for now, when I talk about matrices, think of them over some prime field. Okay. So again, here I'm giving you two matrices, and you got to tell me whether their product is 0 or not, or is the all zero matrix. Clearly, MMB can, if I had MMB, I can solve this because the C matrix is a 0 matrix, right? So MMB seems like a stronger problem. Can anybody see the other way? I claim that MMB is as hard as this. Any ideas? Yeah. It's good. Yeah, that's the idea. So it's very cute. This is due to Kahneman a long time ago, but it's a very simple thing. I can basically break down AB, and so essentially I have two matrices. When I multiply them, the top part is AB minus C. The rest are all zeros. And if they're equal, then there'll be zeros, all zeros. And if they're not equal, then there'll be non-zero part there, right? So for the rest of this talk, we can assume that when we're solving the verification problem, we're dealing with a special case where I'm giving you two matrices, and I want to see if their output is 0 or not. Yep. Questions? Okay. Akshay not left. I guess he's found out I was asking questions and he disappeared. Okay, good. So our main toolkit is going to be fast rectangular MM. Remember, omega was 2.37. This omega perp is just saying that it's the value of, maybe I'll say that in a second. So what do I mean by fast rectangular MM? Here I'm giving you like normal MM is n by n times n by n. Now I'm cutting it to a slice, right? So think of k as something between 0 and 1, like n to the 0.5, square root n or something. I should be able to multiply them faster, right? That's the intuition, like, because it's only easier than n by n. And that's true. Like, this is just fancy math of saying that when I have some k that's between 0 and 1, my running time of multiplying these two matrices is faster than just when I had an n by n matrices. So when I had n by n matrices, my running time was omega. When I have some k, don't worry about what the math looks like. This is just some fancy hippie-jibby. Let's just ignore this. The takeaway is just that when k is less than 1, I have a running time that's better than omega. Okay, and like this is an example of what some of those bounds look like. So when it's 0.321, so if k was 0.321, then I can do this whole computation n squared, which is like just linear. I'm very happy. If k is a little bit bigger, like k is 0.5 square root n, then my running time becomes n to the 2.04. If my k was 1, that's the n by n case, then it becomes omega. And if it's less than 1, it's slightly less than omega. So as long as k is between 0 and 1, I'm going to get a running time that is sandwiched to something less than omega. And so all we're going to do in the rest of this talk is keep reducing our problem to some smaller dimension and apply faster rectangular mm, because that'll give me faster bonds. So the idea is going to just be coming up with reductions. Okay, questions, comments, thoughts? Yeah. This is when like the delta is equal to the so it's how many points you get. It's 1 plus the omega will be omega plus 1 plus the exact value of this. So we 1 will be like n to the 0.5, and you're adding exactly that much over here. So you can define K1 more time. Omega 1 K1. Oh, good. So this is the domain. I should be careful. 1. This is actually, but this is what I've written here is going to actually be 1 K. So 1 is just n by n times whatever the dimension of the third part is, because this has to be n. This is supposed to be n for me to do multiplication. So K is going to be a dimension of the third part. Turns out that 1K1, 1K, all the as long as I permute any of these, it's the same thing. That's a different thing, but essentially it's so I've written this wrong there. This is 1 K. K is on the right. Yeah. Okay.
But the goal is to derandomize Freivalds.
Yeah. We're not going to fully de-randomize, but we're going to de-randomize that sparse case. Awesome. And that sparse case we're going to reduce to fast rectangular minimum. And we're going to, that's the idea. Okay, so we need one more small helper and then we're ready for everything. Okay, so the claim is a very simple lemma. If my matrix has like a to the delta non-zero entries, okay, think of delta as 1.99, right? Just less than n squared. If it has that many entries, then there is either a row or a column that has sparsity n to the delta over 2. It's greater than 0 and has sparsity n to the delta over less than n to the delta over 2. Why? Let's assume not. Let's assume each row has sparsity greater than n to the delta over 2. What happens? How many such rows can exist? At most n to the delta over 2, right? Well, then each of those columns corresponding to those rows will be sparse, right? So when I say sparsity, I mean the number of non-zero elements. Yeah. Sparsity is non-zero. Questions? Yeah. All I'm saying is like imagine I had that. So my claim is if my overall matrix was n to the delta sparse, so let's say n to the 1.99, then I'm claiming that there exists either a row or a column that has sparsity at most n to the whatever 1.99 divided by 2 and is greater than, has sparsity greater than 0. So it's a non-zero row that has sparsity less than n to the 1.9 over 2. And I'm saying that's true because if that was not the case, then how many such rows could I have that have, if all the rows had higher sparsity, then I only have this many rows, this many possible rows. Let me look at those corresponding columns. They should be sparse. All of them should be sparse. Yep, questions? Okay, so let's rephrase our problem again. Our goal now with the also, we were doing verification. We've reduced it to the all zeros problem. So I'm giving you two matrices, A and B, and I'm promising you that AB has at most n to the delta non-zero entries. Okay, I'm giving you this promise because only work on the sparse case, right? Now, so there are two cases. Either it has n to the delta non-zero entries up to that many, or it has 0. Tell me which case you're in. Either AB is equal to 0, or they're at most n to the delta non-zero points. Tell me which case I'm in. Yeah. So I'm saying I'm giving you a promise problem. I give you two matrices AB, and I promise you they're in one of two cases. Case 1, the product is 0. Case 2, the product is non-zero and has at most n to the delta non-zero points. Tell me which case I'm in. Yeah. Okay. Good. More questions? So let's try solving this. This is the same. Now this is exactly the same problem as MMV after all reductions, right? Okay, so what is this problem asking? Well, by the sparse matrix lemma, right? There exists now a sparse row, a sparsity or a column, a sparsity n to the delta over 2. Yes? That's an observation from before. So maybe the question now is, can we detect such a row or column? If we could efficiently detect this, then we're done. Yeah, that's going to be our approach. Questions? It has more than 0, but less than n to the delta over 2. Yes. Yeah. No, it's upper bound on delta. No, I want upper bound on the number of non-zero points, right? Yeah, it is counterintuitive. We'll see this in a second. Like that is the if you're saying intuitively that doesn't make sense, I agree with you. But we'll see that the techniques let us prove the sparse case. We can't generalize the techniques to the dense case. If you're saying philosophically, yes, it's counterintuitive. If you're asking like, but the statement is incorrect, then the statement is at most. Yeah.
Either 0 or like more than n part. It's like either 0 or like less than n part delta.
Yeah.
So how is the zero case different from at most
Yeah.
In the b equals 0 case, I can actually tell you it's equal to 0. So I can distinguish the case when it's exactly 0 versus it has some number of non-zero points, and some number can be anything up to n to the delta. And I can just, I'm not giving any normal. You can choose how many, like you choose whatever you want. Right? So there's one case which is AB equals 0. That's the all zeros problem, right? That's one case. And now I'm saying let's choose anything from 1 to n to the delta. You can choose whatever you want. I'll be able to answer it up to whatever you choose, as long as it's less than or equal to n to the delta. Yeah. Question? Oh, good. We all keep asking questions. This is good. Otherwise, I'll ask you. Nice. Okay. So how are we going to solve this? The idea is we're going to use like linear codes. Okay. And so maybe you guys have not seen linear codes before, so I'm going to give a quick overview. Yeah. Here. Good. Okay. So how do linear codes work? My goal is I want to encode some message. My message is k bits. I want to encode this in n bits. Why? Because by adding some redundancy, I can maybe like recover, the message if something gets lost in transmission. Okay. So the way this works, linear codes works, is I have some kind of generator matrix. It takes as input my code word. It repeats the word, and then it adds some extra redundancy bits at the back. So like now somebody else can later decipher it. So my code words have the form generator matrix times x, and my words belong here from this queue, and now they're mapped to like an n-bit hypercube.
Right. So
Yeah.
see the set.
See the set of all code words, right? So every code word, every word gets mapped to a code word. The words are from in this k-bit subspace. These code words are in this like n-bit subspace. I'll show a picture also in 1 second. And then there's this notion of a parity check matrix. What does a parity check matrix do? It's kind of the code words are like the kernel of this matrix. So if I'm a code word, the output is going to be 0 when I multiply the parity check matrix. And if it's not a code word, then the output's some kind of non-zero item. Right? So it's a way of testing whether I've got something that's a valid code word or it's been corrupted. If it's been corrupted, then I can maybe do some error correction. Otherwise, I'll just let it go. Right? That means I've got the right word. I can just take the word as it is. I don't want to do anything else. The distance of a code word is just the distance between any two code words, like the minimum distance across all any pairs of code words in my space. Just think of like Hamming distance, right? And MDS is just saying like I'm maximizing the distance between any two code words. It's maximum distance purple. And the good thing about all this is that the dimension of my parity check matrix is quite small. So let me give a picture. I think it'll make more sense, and then I'll take questions. So initially, I have like my words in this dense cube. Every point is a word. What I do is I take my generator matrix and transform this into a bigger space, right? And now they're more spread across. Now I argue that this map has even more properties. There's some structural properties, right? I have my code words. Moreover, the distance between any two code words, the minimum distance is at least d. And like kind of what these circles represent is that if I corrupt a word within like d over 2 errors, so the Hamming distance is within d over 2 of my word, I can actually correct it and retrieve my word. So there are a bunch of nice properties that this map gives me. Like that's a picture of what's happening. Yeah. What is d again? D is the distance between any two code words, the minimum distance. For all our purposes, d is going to be the same across. But yeah, it's the minimum distance between any two code words. D over 2 is just how far I can correct. Like up to what distance I can correct errors. So here I can correct over d over 2 errors when my distance is d. Yes. We're going to be dealing with very specific matrix. So, and like kind of the takeaway from at least the first part is going to be, well, maybe you could use these specific matrix properties to get the result. That is true. You can. But the second part, when we go from this verification to actually solving multiplying the matrices, you no longer have so now you have to you're going to use the recovery algorithms like this decoding procedures, and that's going to solve search for free. Whereas if you were just using matrix structural properties, you're reinventing the wheel in trying to define these. Does that make sense? But that's kind of the intuition as to like why like viewing these as codes is going to be more useful than like not viewing the codes and just like looking at these matrix properties that we're going to use. But you're right, it's going to be very structured matrices that represent these codes. Yeah. Questions? More questions? Questions? Okay, so can somebody tell me how I can use this to solve my problem? We have everything now. How do I use linear codes to solve detecting a sparse column? Yes, that is sparse. Yes, we know that one exists if it's non-zero. So how do I detect it? Huh? Good. And what does that tell me? So what code word am I looking for? Yes. What do you want a distance to be in our parity check matrix? What distance do we want our code to have? What should the distance be between two code words? You guys are doing the right things. I'm trying to extract what should the distance be? Like what distance do I want to have? Anybody? Huh? No, it's like Hamming distance. I want what Hamming distance do I want here? +1. +1 because now that'll guarantee that all the vectors. So I know that there's one sparse vector. So like that cannot be if it's plus. So it guarantees that it's not another code word. And I know 0 is a code word, right? So this must be close to 0 and not be another hit and not hit another code word. That's it. That's the idea. Our algorithm is done. I mean, we'll reinforce it a little bit more. But if my distance is n to the delta over 2 plus 1, I'm guaranteed that it's distance from 0. So if I have any n to the delta 2 column or row, it's going to be, it cannot be a code, it cannot hit a code word from 0, right? Because the distance is at most is already at least n to the delta over 2 plus 1. And if it's non-zero, then I'll catch it. If it was 0, then it would have been, I wouldn't have caught it. Questions? Good. So now so we will analyze this in a second, but let me just argue correctness first. So are we convinced that we correctly solve the problem before we analyze the running time? Yes. Is a parity check? Yes. This one. So here I'm claiming that either a row. So we don't know what is sparse. There exists either a row or a column that's sparse. Imagine the product was 0, right? Then whether I look at HAB or HAB transpose, either way it's going to be 0, right? So the one case where AB is equal to 0 will always give me 0, right? Now what I'm checking for, either a row or a column must be non-zero, right? It must be that delta over 2 sparse. Let me just look for that. So the left HAB, I'm looking for the row. In the right, I'm looking for the column. One of them must exist. Now multiplying my parity check by everything, if it like by every single column, one of them is this vector. Which one it is? It's going to output non-zero when it hits it, right? And now we're going to claim that this H matrix is going to be small dimension, and hence we can use our fast rectangular MM to get this for free. So before we talk about the speed, are we convinced that the correctness of the algorithm? You guys derived this, yeah? Good. Okay. So we have an algorithm. Let's argue why it's correct or like why it runs fast. I can generate my matrix H fast. It's just a random on matrix. That's a parity check. That's an example of a parity check matrix. For each one, it's very easy. So you have 50 matrix, and the dimension is going to be n to the n over delta over 2. Why? Because this is a little bit more technical, and I don't want to waste too much time. But if you look at our code example here, my k and my Reed-Solomon code is going to have like k equals. Like think of D is delta over 2, then k is going to be n minus n delta over 2. So when I do n minus k, I'm left with n minus k. It just becomes delta over 2. So that's a little bit of technicality, but yeah, the point is like my dimension is going to be very small. Once I have a very small dimension, I apply the hammer of fast rectangular MM. We're not very creative people. And I get that my dimension is 1. This is 1k1. Remember the question you guys somebody asked? Now the k is delta over 2. And I can apply the associativity of H. So first apply HA, then apply HAB, and I get my running time. You're done. Result 1 done. You're breaking Freivalds to some degree. Nice. Again, like there's nothing technical here. It's all just by some observations and using the right tools. Yeah, questions? Okay, good. So where are we? Went too far ahead. Yeah. So I guess the next result is going to be along the lines of giving you a randomized algorithm that's a little bit more fine-tuned for the number of random bits used. We saw that Freivalds used like O(n) random bits. There's a way of making it log n. We can also make it, if you want to be really like kind of careful about how much you use. The hope here is that you can de-randomize some cases by just brute forcing through the number of random bits if delta is small enough. And so what we show is like if you have some promise of sparsity, we can reduce the number of builds to delta log n over 2. So remember, when delta is equal to 2, the worst case, I use exactly log n, so we recover the result. But when delta is less than 2, we can still get some slight improvements. And the question is, why can't we just use the previous approach? The issue is, I would just like to sample a random row of my van der Waals matrix and say like this is a good tester that like finds like if it's non-zero, it catches it with probability 1/2. This is what I would like to say. However, the parity check matrix only gives me a promise that it'll be non-zero when it's not a code word. It doesn't tell me any promise on the weight of my resulting matrix. So I can't say anything specific there. So I need some stronger guarantee than just yeah. So when I use a parity check matrix, it just tells me that it'll be non-zero. It doesn't give me any guarantee on what the Hamming weight of my product would look like. So if I sample a random row, it doesn't tell me anything. It just tells me that there's a collection of rows that will tell me it's non-zero. So I want something stronger. And the stronger thing I'm going to use is this notion of k-regular matrices. So what does it mean to be k-regular? It means that if I pick any collection of k by k rows and columns, it's going to be non-singular on those k by k points. Right? So now imagine this exists. We'll see if it exists in a second. Let me replace my van der Waals with a k-regular matrix, right? So I have my AB minus C matrix over here. I'm now going to multiply it by some, before it was a van der Waals matrix, my parity check matrix. Now I'm going to use a special matrix that is every k by k submatrix is non-singular. It has an inverse. Okay. Now, because every block is non-singular, how many columns can I have with Hamming weight 0? At most this, right? Because the minute I sample and enter the delta over 2 columns, I get a full block, and I have if it's non-zero, I can't have a zero product, right? Otherwise, I'll break the inverse property. And so now I just have to find. So now instead of multiplying the whole matrix, now I can sample a random row. What happens? Well, so if I have this many rows, I know that only that many columns are 0 at most. The probability of success is 1 minus me sampling a bad row, which is just at most this. Number of bad rows by total number of bad columns by total number of columns. Very elementary. And that's greater than 1/2. I repeat this a few times. I'm done. Okay. So the only question left is, do k-regular matrices exist and can I generate them easily? Turns out they do. An example is a Cauchy matrix. Okay, you might have seen this in real analysis. And Cauchy matrix is not only k-regular, it's super regular. What that means is it's like not just every k by k, every 2 by 2, every 3 by 3, every 4 by 4, up to any n by n is also non-singular. It's a much stronger property. And what's, I guess, again, this coding theory perspective is that if you look at this generalized Reed-Solomon codes for people who know codes, the S in like, so this is the generator matrix in its systematic form where I message plus redundancy. This is actually a Cauchy matrix. So it's if and only if. So these also come out of codes, right? Like, yeah. No. You can do this over field. Yeah, I think so. I have to double check, but I'm pretty sure. Yeah. Yeah, more questions? So once you have this, the algorithm is the same, right? I just multiply. Yeah, I need all of them. So my field has to be big enough. Just imagine like whatever it is, you can create a field extension and just work on the field extension. See that?
Yeah, large characters.
Yeah. But whenever your field is small, just work on extension. It doesn't like it'll cost you log factors, but I told you earlier, I'm a complexity person. We don't care about log factors. Yeah. Okay, good. So randomized algorithm is going to be identical now. I'm just replacing instead of multiplying with the whole van der Waals matrix H, I'm going to sample a random column from this Cauchy matrix, and I'm going to get the answer. But my analysis is exactly the same. Okay, questions. Okay, good. So let's look at kind of like, let's compare things a little bit. So here's like the original. So let's do deterministic first. Here's the original matrix multiplication, n to the omega, does no randomness. Then there was this paper by Kuhneman where he said, like, look, we can actually solve a sparse case. My running time is going to be this. But we saw that omega is 2.37-ish. So when delta already gets to 1.3 or 1.4, already I'm kind of screwed, right? I go over n to the omega, which is my brute force. We improved it to this running time. So as long as delta is not equal to 2, they're always going to be smaller than n to the omega, right? So we just extended this result to n to the 1.99999, however far you want to go, right? In the random case, I could just keep sampling. That takes this much time and uses a lot of random bits. That's not the most efficient way to go. But then there was Freivalds who came up and said, like, look, here's the thing that runs in n squared time. You only need n random bits. And then there was like the first optimization, which you went to log n, and then we optimized a little bit more. But this is maybe not so good. That's kind of the state of the art versus what was known before. Okay. But let's go back and think about this in a more philosophical sense. So yeah.
I did settle a parity of the between codes to be m power delta by 2, like why not make more?
Because then the dimension becomes too big. And once my matrix dimension becomes too big, then I cannot use past mm anymore. Yeah. So the whole point is I'm balancing between using the rectangular mm and using the. Good question. All right. So this is now back to the more philosophical point, which is if I told you two things disagree, which is the harder case to find? The case when they disagree on one place in a big space, or the case where they disagree on many places in a big space, right? Most people think needle in the haystack. If I ask you to find a needle in the haystack, this is the harder problem than finding hay in the haystack. However, what we've shown with this result is that for this kind of problem, so I guess we're not the first people. Kuhneman first showed that like if the matrix, like if they disagree on one end of the 1.36 points, then you can solve this faster than n to the omega. We generalize this even further. We say that if actually they disagree up to n to the 1.99 points, we can solve this. If they disagree on 1.2, 3 points, we can solve this. The case that's hardest for us is the case when they disagree on many, many points. That is, I give you two matrices A, B, and C, and they disagree on epsilon n squared points. That is almost every random point you sample, they disagree. This apparently is the hardest case of deterministic algorithm. However, this has a very trivial randomized algorithm. Just sample and take a look, right? I sample a few points, I sample a constant number of points, and I just verify, because verification is easy. I just do a computer dot product and see if it's correct or not, right? And I don't even need to look at the matrices in some ways. I'm sampling without looking at the matrices, right? It's like a black box algorithm. It's very counterintuitive, but it's also natural in like all these de-randomization problems where you reduce it to find like PITs like this. All these problems are like this, whereas finding hay in a haystack, and instead the hardest case is not actually the case where I'm searching for something specific. It's actually finding this thing. Because when there's something specific, you can use a structure to like gain something. Like in this case, use a sparsity. When it's a random point, you don't really have any strategy to search, right? So what are you going to do? You have to just keep trying till you hopefully hit something. All right, questions. So I guess like I give this cartoon at the end, which is I'm giving you this elephant who was in a party, but the elephant is so big that he's kind of he's across the whole many different rooms, and so nobody sees the whole elephant. And so he's claiming that he was there, but nobody can verify that he's there. It's kind of the same thing. Our non-zeros are like this elephant in this product, and we're like looking for this. We can't find it, and I mean, it's not directly translates, but at least the intuition is there. Okay, so that's verification. After this, no more verification. Questions before we move forward? Awesome. Okay. So when you have a hammer, everything's a nail. And so we saw this working here, and we said, how do we can we squeeze more out of this? And so what's the most natural question? Okay, we solved this verification problem. AB equals 0 versus, like, what if I want to just multiply AB? If I promise you that the product is the output is sparse, can I just multiply two matrices faster than n to the omega? Okay, can I get faster matrix multiplication algorithms when I promise you the product is sparse? And it turns out that these ideas almost naturally generalize without much work. Okay, so I'll give you the theorem statements first, and then I'll quickly see how they look like. So the deterministic algorithm is going to be, I give you matrices AB. I promise you that the product has at most n to the delta non-zero entries. I'll now compute their product. in the same running time. I'm just going to modify my algorithm a little bit. The other algorithm we're going to see is I'm going to give you a randomized algorithm doing the same thing, but it's going to run even faster. And I'll literally give you intuition as to why this is almost optimal. Like we probably should not expect to do better than this. Yeah. Oh, whenever delta is greater than equal to 1. When delta is less than equal to 1, you already can like do some other tricks. When delta is greater than equal to 1, you just yeah, imagine just okay. For example, like when delta is greater than 1, just use the let someone use the deterministic case. And then when delta is greater than 1, use the questions of theorem statements. Yeah. So how are we going to do this? Our intuition comes from this notion of compressed sensing. I don't know if you guys have heard of this. It's used in like our cameras everywhere we use this, where I give you some parameters m and t, and my goal is to compress. I have a t sparse vector, right? I want to compress it into like think of a picture. It's generally very sparse. I want to compress it into less space, into a smaller vector, where I have n bits. My vector is t sparse and n bits, and I want to compress it down to like m bits. So m is less than or equal to n. T is a sparse vector over n bits. I want to compress it. So I have two parts. I want to find a compression matrix H that compresses my t sparse vector into something smaller, only m bits. Maybe it's dense now, and a recovery algorithm that extracts from my compressed vector the actual sparse vector t. Right. So I should be able to recover. So picture like I have a compression matrix. I have my sparse vector. It gives me some new sparse vector that I can now recover E anytime I want to. Questions about the definition? Yeah.
Sparse is like
I have t non-zero points in my vector. When I say sparse, I mean like that the number the before is the number of non-zero points. Yeah. Okay. So for now, let's just assume that every column of the product was sparse. Let's just believe that. Yeah. Question? Yeah. I can go. Good. Okay. So let's do a special case where every column was sparse. Let's for now. I mean, this is maybe not real. Let's believe this for a second. What do I do? Well, now my algorithm is easy. I just construct H, and let's assume we can do all this also very easily. I construct H. However, I do that. I now multiply H times my product AB, right? And then I apply my recovery algorithm on H times AB. And now I'm done. So let's like there are more to a bunch of details. This is the framework I want to show. If every column was sparse, I just multiply by my compression matrix. Hopefully, it's a small dimension. And then I apply my recovery algorithm on it, on every column. Yeah. So when I do R here, I mean like on every column of this matrix, I'm applying my recovery algorithm. Questions? Yes, we're going to get there. Yes, absolutely. So now I'll tell you the requirements, what I need. Yeah, good, you're ahead of me. So let's analyze the running time of this, like just as a meta framework. What do we need? Well, number one, what is the time it takes to construct H? This has to be this. Let's call this T1n. And two, the running time of the recovery algorithm. Exactly what you're asking, right? If I have these two, what is the running time of my algorithm? Well, for now, let m be some polynomial function, sublinear function of n, right? This is my running time, right? I first construct H in T1 in time. Then I do this multiplication. That takes omega k11, right? And then I multiply for every row. I have n rows. So every column, I have n columns. I'm applying my recovery algorithm. So if I can somehow get this whole parameter to be small, I'll be happy. Yeah. This is my framework. Now I'm just going to convince you that I can do all these things. That's it for the rest of the talk, for the rest of this part. How much time do you have? Like 5 o'clock, yeah? Okay. Just tell me like 5 minutes before, then I'll start going full speed. Okay. So I'm going to first convince you that I made an assumption here that every column was sparse. I'm going to say that's fine. We can make that assumption. Why? Let's prove this. This is going to be almost exactly like our sparse lemma before. What happens? Like imagine. So here's kind of just the construction. I'm going to first apply my recovery on C prime is going to be me applying on the whole matrix AB. And then I'm going to apply on AB minus C prime. And I'm going to claim that the C equal to D plus C prime is the answer. This is a lot of words. So what I want to claim here is that D transpose is AB minus C prime. If I can convince you this, then C prime and C prime gets canceled, then I'm left with AB. Okay? And so I'm first computing C prime, which is just applying first H on A times B, and then applying my recovery, and then applying H on AB minus C prime, and then apply my recovery. So I'm only doing the algorithm twice. So it doesn't have any, it's just like 2 times whatever the running time was. So I'm only taking 2 passes. I just want to convince you that actually what I'm computing here is AB minus C prime, and that these things cancel out. You guys with me? So let's see why this is true. Yeah,
We
yeah.
already have C. We are.
We don't have C. We have AB. We want to compute C. Yes. Yeah. The problem is I'm not promising you. I'm saying that in the previous case I said that every column was n to the delta over 2 sparse. Now I'm telling you that the whole matrix is n to the delta sparse. So I don't have a promise on every column. Right? I want to claim to you that that's okay. Even if every column is not sparse, I can reduce it to the following case. So now the whole matrix is sparse, but every column is not sparse. So there could be some heavy columns. Okay, so now we'll see why that's not a concern. Well, if there are heavy columns, all the light columns will be recovered in the first step, exactly to your point. Right? If my column is n to the delta over 2 sparse, I've recovered it. Right? So when I subtract AB minus C prime, those parts become 0. Right? Those columns become 0. The guys who were non-zero, maybe I've increased the number of non-zero points in them, doesn't matter. But how many such guys could have existed? How many such columns, how many heavy columns could have existed? And to the delta over 2, same exact argument as before. Right? So now what do? I work on the transpose. Right? Now that all the rows must be sparse, I'll work there. Same idea. I need only 2 passes. Right? So now again, we've gone from the assumption that every column is sparse. We can live with that assumption. It's not a bad assumption. So now we have to now we have to do all this other T1, T2 stuff, but we've guaranteed that every column is sparse. Questions? Not any questions, Srinivas. Okay. Okay, good. So the idea is going to be that we're going to take this good linear correcting code and convert it into a compressed sensing scheme. Okay, so we saw how the compressed sensing scheme gives us like a framework to solve. We're going to take the properties of a good linear code. I'll tell you what they are in a second. So I'm saying this good linear correcting code, what that means. But that means something. I'll give you some properties. If I have those properties, we prove that we can construct a compressed sensing scheme where we have the following properties. There's a matrix of small dimension, 2t times n. Think of t as n to the delta over 2. Okay. It can be computed in n squared time. Good. And the recovery algorithm is fast, runs in open time. So we get all these properties. We'll analyze the running time in a little bit. Yeah. Because like you were saying, we want fast recovery, right? If our recovery is not fast, then we'll our running time. Yeah. Here. So I mean, okay, if you want to be really, you can do like n to the 1.3, but then now you depend on omega, right? So your result will break if omega goes.
No,
Yeah. Oops. So once we have a good, so my claim is, so we prove that if you have a good error correcting code, you get a good compressed sensing scheme. That's what we prove. And they have all these properties. We'll see the running time of these will be all nice. They'll come later. So what does it mean? What are the properties we need from a good error correcting code? So what we need is very simple. I should be able to compute the parity check matrix in n squared time. I should be able that the minimum distance between code words should be greater than 2t. And I should be able to recover. Like if I have at most up to like t over 2 errors, like if I have up to t errors, I should be able to recover. Right? And now I'm doing exactly kind of the same idea. Like I'm recovering my sparse matrix. I've had the 0 vector. I want t over 2 far away. I'm just recovering that to get my answer. And this is where you can ask, maybe before you could have told me, Karthik, do you really need all this like coding theory nonsense? Like, why do you care? Well, now I'm getting it for free. Right? Why should I have to like recover this recovery process that they're doing after so long, after so many years? Doing it by scratch is too painful. I get this for free from codes. Right? That's where codes are useful. Right? This framework has already existed. Maybe you can prove this by the principles of linear independence and matrices, but that seems like a lot of work. Yeah? Okay, and generalized Reed-Solomon codes are perfect. They're good linear. Like the hardest part for us in solving this problem was realizing what properties we needed. Once we had that, like finding something that fitted was very easy. So we didn't even have to construct, in the beginning we thought we had to construct our own codes, but turns out that like for the properties we needed, even like simple like generalized Reed-Solomon codes are good enough. And like if you don't care about codes, like just a Van der Waals matrix, that's all we're doing. We're multiplying by a Van der Waals matrix, and then we're using some black box decoding procedure on top of it. And so when you set t to be equal to delta over 2, like the bounds kind of follow. Right? Questions? And we match MMV. So like you can think of MMV as a decision problem, and now this is a search problem. MMV asks you to distinguish the two cases. Now we're actually solving exactly if it's sparse within that point, we're giving you exactly what the vectors are. Okay, questions before we move to randomized. You mean like you think it's possible? Yeah. Good. Yeah, but it's weird. So maybe in some ways you could think that maybe the reason why the sparse case is solvable is because maybe you inherently are doing some computation. Maybe I don't know. Yeah, but yeah, this is far less counterintuitive. This is more like more intuitive, I guess. Yeah. Okay, so the randomized one is just more of a. This is just like kind of when you have a paper, you have to make it more readable, or like I guess more fancy. You add more details. This is nothing too fancy. You know, all we're saying is so we steal from another paper. What they say is if I give you two matrices A B, here's a randomized. There's a randomized way of estimating the number of entries per column. So you get like a 1/2 to like a 1/2 to factor 2 approximation. It tells you how many non-zero points there are. We'll now use this to bucket our columns into batches. And now we'll kind of do some switching. So let's see kind of what that looks like here. So like this is for free. I can get the column estimates in n square time. I got that for free. Now I put them into different buckets. I have log and possible buckets, right? Because I'm going from 0 to 2 to the j. So imagine this is like a for loop. I don't care about log factors. So I only care about one iteration. We're going to analyze only one iteration. In each iteration, I'm computing a random one. I have a j here, but you can think of the whole random one. I'm computing 8j times a. Random ones are like fast Fourier matrices. I can multiply them fast. So like even if I don't really care about anything special about rectangles. I can just multiply this part first just because it's a random one matrix. I don't need to analyze this. Because random one matrix multiplication is n log n, and n square log n. So the main cost is computing this bj part. What is bj? Bj is a collection of columns that match this bucket j, right? So how many columns are there? That's going to be our omega, right? So let's say that I'm in bucket j, 2 to the j, and let that be some n to the gamma, okay? Now, Now, how many? So I have the left gamma, which is just my h, but that can be 1. I don't really care so much about that. How many such columns do I have of this sparsity? The bigger my j is, the fewer my columns are, right? I'll always have, if my sparsity was delta, how many columns can I have with that sparsity? Delta minus gamma, right? N to the delta minus gamma, right? Because the total will become delta. So this is my formulation. It'll be like 1 delta minus gamma. Now this is maximized when gamma is equal to 1. So I get my running time is just 1 delta minus. This is just a small trick, like on top of. I think the core idea is the previous part. This is just some kind of added machinery on top of it to make it. But it's interesting, and we'll see why in a second, because this is much faster than the other approach. So one way of de-randomizing is maybe constructing these column estimates in some deterministic way. You could come up with like I see I've made a few randomized algorithms people, so maybe you can come up with a way of de-randomizing this question, and like say if you could come up with a deterministic algorithm, then you would probably de-randomize this whole like computing sparse possibly. And this is like, so there's another paper by these guy in Soda last year where they got the same bound, but they use very different techniques. They use like independent hashing, a bunch of pairwise independent hashing, and some other techniques. So they were trying to get like, as a function of input plus output, they were trying to get like they want a linear answer, a linear runtime based on that. So there's a very different algorithm. Okay, so why do I claim this is optimal? Let's see. So I claim that if there was a faster algorithm for this where output sparse that would imply a faster algorithm for rectangular matrices, multiplying rectangular matrices of this form when delta is greater than 1. Why? So let me take an instance of rectangular matrix multiplication. I'm going to reduce this to OSMM. Does anybody see reduction? This is not hard. Yeah, so I'm claiming that if I had a faster algorithm for OSMM, like I want to claim that it's currently optimal up to where it is, up to its runtime. I think that if you give me a faster algorithm for OSMM, what we just saw, then I would give you a faster algorithm for rectangular matrix multiplication, which is a much harder problem. It seems like the core of our result, right? Like that seems like a much harder problem to tackle. So how do I reduce this to OSMM? Just add zeros. Now what is the sparsity of my overall matrix? Like all in my product, all these columns are going to be zero. How many ones can I have? Or non-zeros can I have? This times n is greater than delta. This is an instance greater than. So that's it. Right. So I can't like anyway. Very trivial reduction. So the point is like if you could come up with a faster algorithm, you imply a faster algorithm for rectangular MM, which we already saw. That's the whale. We're not touching the whale. We're going around the whale, right? So we don't want to touch the whale. Good questions. So that's it. That's multiplication. We're done with multiplication. Now we'll do some. I'm a complexity person, so I have to have some complexity in there. Let's do some complexity, and we'll call it night. Okay. So have you guys heard of SCTH hardness? Should I give a quick rundown? What is SCTH hardness? It's kind of this assumption that SAT requires exponential time, right? So maybe you've seen at a distance or these problems. At a distance, you might have seen just in college, you have this n-squared algorithm for computing. I have two strings. I want to see how many adjustments I can make, so I get one string to the other. There's a very nice DP algorithm that runs in n-squared time. You can ask, can I improve this to n to the 1.99? Turns out if you could, you would come up with a fast algorithm for SAT that is better than exponential time, or like better than the worst case exponential time. Now the assumption says that there should not be any algorithm that's like it's a strong hypothesis. Most people don't believe it, but it's enough to like give you conditional lower bounds, right? So you can maybe say like we saw that the picture of like the bounds on MM, right? And it's kind of stagnated, right? Like improves just a little bit after a certain point. You can ask, well, is there maybe the reason why you can't come up with a better algorithm? The fact that coming up with faster algorithms would imply some kind of fast algorithm for SAT, and like is it maybe SCTH hard to do something like this? That's it. So we show that actually we cannot prove it's like a barrier to a barrier. We say that cannot be true. Like if you could prove that MM is SCTH hard to prove like better bounds for MM, you either will get a superlinear circuit lower bound, or you'll get an explicit construction of a rigid matrix. These are two things that we believe to be true, but we have no idea how to construct, right? So it's just saying that if you could do this, if you could solve this, you're doing more than just this. You're doing a bunch of other fancy things, right? So it's not like to dissuade you. It's just saying that you're not just doing one thing. You're doing a bunch of things that we don't know how to do yet. So it's kind of a barrier to like being able to prove this. Okay, this I'll skip the proof. It's maybe more technical, but essentially, you first either argue that the matrices you get that have to be big. Okay, I'm trying to see. I only have 5 minutes, right? Maybe I'll skip the proof. I'll just leave this as this is, and I'll jump to open questions. If there are questions, you can ask me offline. Okay, so I'll skip this here. Blah 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 blah. Okay, so open questions and we'll end. Full determination of Freivalds. We dealt with the sparse case. Everybody here agrees that the sparse case seems like the hardest case. There must be something. Maybe like you guys are all a lot of graph algorithms people here. Maybe we can represent A and B as some kind of graphs. There's some kind of property going on between them, like some two-path or something. Can we say something interesting about like maybe you can use use the fact that it has some dense graphs or dense plots, some property there to kind of search for something. And maybe there are some more heavy, like we've used very like trivial algorithms. Maybe there's like some heavier algorithms because now we've reduced it to a special case. The product of AB must be dense, right? Can you now in this special case solve here? Maybe. So this is something I think that's open. The other one is Boolean MMV. So Boolean matrix multiplication is just the ors of ands. In this one, we no longer have like, so all the proofs went by AB minus C. There is no minus in Boolean, right? So none of the proofs work. So even Freivalds doesn't work for Boolean. We don't know anything better than multiplying the matrices fully. So can you maybe, at least in the Boolean case, come up with a randomized algorithm that's better than brute force? Yeah? Okay, I'll stop here and I'll take questions.
We are guaranteed like the other kind of promise. If we are guaranteed that product is extremely dense, then like are there algorithms?
Well, then you can just do randomness, right? Like you just sample a randomized deterministic. Oh, no, deterministic you don't know. Randomized, yes, trivial, right? Just sample. Deterministic, no idea. Questions?
But penetrating codes, like we use the distance of n per delta value. But like, what's the maximum distance can get? Like, in general for any peripheral.
Parameters, whatever you want. The problem is like the problem is just so in this case you take these parameters just because of the dimension.
Yeah, sure.
So, but like really, when you would decide, you can choose the like you can pick the parameters. Like for example, here we're picking our the number of redundancy bits to be very high and the message to be very small. You could also pick it to be very like your redundancy bits to be very small, in which case the distance it purely depends on the parameters you want. I mean, there are some of these like singles and bounds and all the other you got to keep track of. Like there are some worst case upper bounds and all, but it's not. You get to choose this. More question?
Could we expect ETH hardness or?
For this?
We have set, we have conditional on set hardness. But
Yeah, like our rules don't apply to ETH, so it's possible. Like you might get some weaker value, we not all of them, but I don't think so. I think you can probably show ETH sharpness of them. I mean, if there's a way of showing. I don't know. I think like the way this is, it's probably more likely to be true than not. So it's probably true that you can come with an S square MM algorithm and not be able to improve SAT. Like that's a much more likely world to live in than the fact that MM is ETH hard. At least for me, I feel that's my intuition. Yeah. Questions? More questions? More questions?
So if AB themselves are sparse, what is it?
Oh, okay, I didn't do that in this case. So we handled that also. Like if AB, that just makes it more complicated. The point is there's this Euster's Wick. They had this paper a long time ago where they can multiply sparse matrices. And you can apply that same analysis into this, but now already it's like a little bit messy. Now imagine like handling this input sparsity also. You can balance the input sparsity to the output sparsity. And then you can balance it so that like first you do some level of input sparsity analysis and then you do output. But we can handle that case also. So I think yeah.
So
Like-
what's the running time?
So it'll just be like there'll be a parameter alpha where alpha is balancing the running time of running the input sparse stuff versus running this delta over 2. And it's minimizing between those two. And alpha is some like weird convex function that we don't know how to analyze. It just this is the optimal balancing parameter, so we call it alpha.
Yeah, but if we are, I mean, like we dealt with the case where like C is delta par, n par delta sparse.
Hmm.
Like if let's say A is n par delta sparse
Mhm.
and B is n par delta sparse,
Okay, for that regime you ask
then will we get a lower running time?
yeah, it'll be lower. Yeah, it'll be lower. I mean, up to some threshold, after which like if delta becomes too big, like let's say it's 1.9, 1.9, 1.9. I think there's some weird like graphs, like weird drawing this back there. It's very wonky because omega is a wonky function. But yeah, for the most part, you get low running times. So when you handle that, that's why we handle both. Right? When you handle the input sparsity too, it doesn't put your running time over. Basically, the point is like, what do you do first? You first do the input case, the input sparse case, and then do the output sparsity part, or do you do the other way around? And that's what you're trying to decide with the. More questions?
Now let's end the speaker.
What is this?
Yes. Okay.
Oh, wow. Thank you.